Welcome to this product demonstration presented by the team from Kingsmen Software. Meet DeepCrack, the future of structural analysis, where AI and computer vision converge to safeguard your structures. This innovative tool meticulously identifies and monitors divisions, clefts, and cracks across various materials, providing a relentless, unblinking sentinel for structural integrity. DeepCrack doesn't just detect flaws, it analyzes them, utilizing pixel analysis to track their progression and alerting you to potential damages and prepare opportunities before they become critical. Ensure the longevity and safety of your structures with the vigilant eye of DeepCrack. Now, I'll turn it over to today's speakers to show it all in action.
Welcome to DeepCrack. We are the rover team. We are actually 75% of the rover team. My name is Kevin. This is Parker. This is Monica. We are so excited to talk to you about DeepCrack today. What this is our artificial intelligence image analysis tool. So some months back, we received kind of a challenge. We're going to be telling you about that. We're going to be telling you about how we met it. And in the process of that, we're going to talk about AI computer vision. It's going to be very fascinating. Then you're going to see the really exciting stuff, and that's when Monica's going to show you a demo, and Parker's going to show you about some of his work too. So, a lot to cover. We'll get right into it. Our problem statement. Buildings are tall, can't climb them. It's really hard to see cracks in the walls. The use case that we are building our project around is the idea of an AI drone washing a building, being guided by video, taking lots of images, and what we want to do is say, if we have an image that has a crack in the wall, can we identify that crack? And if we have two images of the same wall over time, can we tell if that crack has changed? Now, in order to do that, we use AI vision. So this is where we get right into it. This is the first one, image classification. This is applied AI vision technology. Imagine you are a teacher and the AI model is your student. You hand them this picture, you say, what's in here? I got a person, has some sheep and a dog. That is image classification. It's just telling you what is there. Getting a little bit more complex, object detection. Now we're looking at the specific objects. We're drawing boxes around them to define where are the pixels that make up the sheep, where are the pixels that make up the person, the dog. Also, we're categorizing the sheep together, but we are also noting that they are separate objects. Now we're getting into image segmentation. This is a more complex layer of that image processing, the intellectual process of seeing things. Now, this is the AI version of paint by numbers. So, background's a big bright spot color. We have our sheep, they're all blue. Our dog is red. Person is turquoise or aqua, and not a color person. So this kind of gives some context to that image. So the AI model, your AI student, is starting to build broader understanding. And that's where we come to common objects and context. Now, you can see we've painted around here, so we've got the sheep are all different colors now, but we still think they're all sheep. We know they're separate. Person is still there, the dog is still there. We are also observing the context of the image. So it's not just a person, a sheep, or a series of sheep and a dog. It is now distinguishing each individual thing. So that is the very quick overview of AI vision. Now we're going to jump into the demo. That's where Monica's going to take over.
So this is my agenda for the demo. I'll be demonstrating object detection and segmentation using a web application. I'll be showing you how these detection models can track objects on images, videos, and live streams, and also be demonstrating crack detection using a custom model, which can detect cracks on a concrete wall. So our main goal of our project is to detect cracks on different materials, because the drones would be taking pictures of buildings made with different materials. So I'll be sharing my views on how we can train our own model in such a way that it could detect cracks on any given material, whether it's a crack on a concrete wall, a brick wall, or a window crack. So let's get into the web application real quick. So this is a web application built on top of an open source framework called Streamlit. Streamlit is a popular framework for computer vision applications. So if you look at the application, if you look at the left panel, so I have three models for the demo, object detection, segmentation, and crack detection. And we also have a few sources here, image, video, webcam. I'll be starting off with the object detection, which is pre-selected here. And I have the image source, which is pre-selected. So I'm going to quickly upload an image. So you can see I just uploaded an image and I'm going to do object detection. I just clicked on the detect object button. So you can see, just like how we saw in the PPT for the object detection, you can see it's able to identify the object. It also provides a bounding box around each object along with the name of the object as well. So you can see the chair, the person, the laptop detected here. So this is object detection. Now moving on to the next model, which is segmentation. So I'm switching the model here and I'll be using the same image, and then I'm going to click on detect objects. So and we'll see the difference between these two models. So segmentation goes a bit further. It does the same thing as the object detection. It identifies the object, provides a bounding box around it, and also the name of the object. But it also provides the shape of the object as well. You can see the shape of the person here, the shape of the laptop, and each object has its own color on it. And it's weird, it identified the boat as a cake. So
There's a 64% chance.
yeah. And probably it's a cake. They don't want the kids eating that cake, so that's why they had it there. Anyways, now let's try segmentation on a video. I already have a video uploaded here. It's just two people working. So I'm going to detect objects. So I'm going to click on detect video objects. So now you can see, so it's the same thing. I tried the segmentation model on this video. You can see the person identified, the bounding box around him, and also the shape of the person. It's the same thing with the other person, and you can see it's trying to identify the potted plant in the background. And that has a different color, and yeah, I see there's one more there. Now let's try webcam with the same segmentation model. So now I'm going to click on detect objects.
Laptop.
Sorry.
Oh, person.
Yep. I'm trying to, I don't see that. Anyways.
Apparently Bill's an Android.
Yep. So you can see it's trying to identify the phone. Yeah, it got another one.
That's cool.
Okay. So now these models, object detection and segmentation, they are pre-trained models trained on a large data set. When I say large data set, it's nothing but an inventory of images filled with different kinds of objects in it that we use in our daily lives. So these pre-trained models cannot detect a crack because crack is not an object. For instance, if I go back to object detection, go back to image, and try uploading an image. So this is an image of a crack on a concrete wall. So if I try object detection on this image, I'm clicking on detect object, you can see it's not able to detect because it's not trained to do so. So for this use case, we would need a custom model, which is trained on using a custom data set. So I found a data set online that had images of cracks on a concrete wall. So I used that, I downloaded the data set, and then I trained the model, and then I integrated that model into this application. So now for the same image, if I switch to crack detection model, and then if I try to detect objects, you can see it's able to identify the crack. We also see the bounding box around it and also the shape of the crack. Let's try uploading a different image. Probably this one. So this is again a crack on a concrete wall. You can see it's able to identify the crack. So, but there is a limitation for this model. It can only detect cracks on concrete walls. For instance, if I try uploading a different image, so this is a crack on a brick wall. So if I try crack detection on this image, you can see it's not able to, because it's a very limited model that is only trained to detect cracks on concrete wall. So for our use case where we have to detect cracks on different materials, there are two ways we could achieve it. One is build a large data set filled with different kinds of cracks on different materials and then vigorously train the model so that when we get the images from drones, we should be able to detect the cracks on any given material. The other approach I had was combining different models. So this is a different model. This is called image captioning model. What it does is it basically extracts information out of an image. For instance, you can see astronaut riding cars in space, and a red stop sign with a white border and a building in the background. So it basically extracts information out of an image. So let's say if I try uploading the same image, the brick image here, and then submit.
And what we're seeing here is the application of that last layer of like the AI vision. It's not just looking at the objects, it's not just segmenting them, it's not just defining where the pixels are. It's thinking about the whole thing. It's processing it like you do when you look at a picture. It's like you're not just looking at a crack, you're looking at a picture of a wall with a crack. Or in this case, a brick wall with a crack and maybe some graffiti.
Yeah, so you can see the text here. So it says a crack in a brick wall in a building. So this, like I said before, it basically extracts information out of the image. So what we could do is for the second approach, we could use this as a top layer. We could extract the information from the drone image, identify whether it's a crack on a brick wall or a window or a concrete wall, and then we can have different data sets, different models for each material. So let's say if we extract the information, if we identify it as a brick, then we'll be calling that model that is trained to detect cracks on a brick wall. If it's a concrete, then we'll be calling a different model. That way we could probably achieve accurate results. So that's the second approach. So that's all about crack detection. So that's all I have. I'll be passing over to
Great.
Parker.
That's me.
I
I'm
was-
Parker.
I was about to say passing over to Rover.
I am a rover as well. All right, can you take me back to the PowerPoint,
Sure.
please? All right. So obviously, once we have identified a crack in a building, the next thing we would want to do is, over time, can we check if that crack is getting bigger, or if it's been repaired, does there crack, or are those repairs holding? So to answer that question, we actually have to go back to the very beginning of our project. Kevin Carney came to us with this image of a sushi dinner from a children's activity book and asked if we could write a program that found the differences between these images. Now, real quick, we're not going to stop here just to figure out where the differences are. You're welcome to pause the video and look. But to accomplish this goal, I wrote a program that checks the two images, and it looks through them pixel by pixel, line by line, and compares the two. And if it thinks that the pixels are the same point in real space, then it makes a note and defines it later. So here's what my program is able to define. You can see that some sushi is missing from the top. One of the lines on some sashimi was gone. Some sesame seeds are gone. We've got a piece of tuna or some fish. I don't eat fish. I don't know what it is. But yeah, it's pretty accurate. And it was able to find a bunch of stuff. But obviously this is a doctored image. Someone went in with Photoshop and removed things so that they could maintain the similarity between the two photos. In real life, this is not a realistic scenario. So we had some of our employees offer to take photos for us to show the differences in a wall repair that they had. So you can see on the left is before a repair and on the right is after the repair. You can see that in real life it's very difficult to take the same photo twice. We asked one of our employees to take that photo and they screwed up royally. There's a lot of differences here. You can see there's differences in pitch, angle, depth, the time of day is different. There's shade coverage on this after photo. There's even one of these bricks right here in the middle was painted. So there's a lot of differences between these two photos. If we really wanted to compare them, it would be very difficult to do so. But this is where we started. We started the process with a worst possible case scenario. We wanted to filter out a lot of data because what we're starting with is just an excessive amount of data, and then we are filtering through all of our steps to achieve our end result of comparing the two photos. But for today's demo purposes, we're going to show you a little bit of a nicer version. Here we have a before and after photo of our CIO, Denise. Denise, our CIO, wanted to mount a TV in her backyard and said, hey, I can take some photos for you. And we said, great, please draw an X on the ground so you can stand in the exact same place and try your hardest to take the same photo. And Denise did a really solid job. But you can see here that it wasn't quite good enough. Like, even if she's trying her hardest to take the same photo, it's not exactly going to match up. You can see that the grout on the top left shifts a little bit, and we are losing some of the brick on the bottom. So this is a suitable place for us to start, but it is still very difficult to compare these two images if you wanted to compare them directly. So essentially what we have to do is stretch one of these images to meet the dimensions of the second image, and we use a process called image registration for that. The technical definition is the process of transforming different sets of data into one coordinate system. Really, that's just a very complicated way to say we're taking a first image and just stretching or shrinking it to meet the dimensions of the test image. So you can see here, if we're looking at a heart and we really want to just look at the movement of the heart, we actually have to freeze the rest of the photo so that we can simply see the image of the heart moving. So what's actually happening is a lot of the photo is stretching inward. And to start this process, we do what's called feature matching. So the program's first step is to go through each photo line by line, pixel by pixel, and determine if it's the same point in place or point in space. And if the program believes with above 90% certainty that it is the same point in time or same point in place, then it draws a line between the two photos. You can see a lot of these on the left are lining up pretty much straight across. Like right here, it's pretty certain that a lot of these are the same, but we are getting some huge diagonals right here, and these are a lot of false positives because there is so much excess data with this process. So we have to filter above a 90% on about 6 or 7 steps, with this being the first step. So after we have done our feature matching, we're then able to warp our test image against our query image. And that looks like this. So here we have our test image, and we have stretched it to meet the dimensions or the look of the query image, or excuse me, the test image. No, it's the query image. The query image. You can see here we are adjusting the after view so that we have moved this grout line to be a little more level. So we've lost some data along the top, and then we're actually chopping off a good bit of the brick on the bottom. But this is what the program thinks is its most accurate depiction of the warped image. So after we have warped our images, we can then calculate the absolute difference between the two photos. So here we have both photos layered on top of each other and then converted to grayscale. What you're seeing in the absolute difference is areas of light or values of height change. Dark or black sections would be areas where there is no change between the two images. So it's pretty much exactly certain that the pixels line up correctly in these dark areas, and there are high amounts of change where there is white. But obviously this is a very noisy image. If we were going to feed this directly into the end result, it would find that there's a lot of changes just based on these small pixels. So what we have to do next is apply a threshold. So again, anything above, or excuse me, anything below 90% of a certainty is removed from the image. So now we have just complete darkness where it's pretty positive that the image is the exact same. And then we again have our holes in the wall. And then we also have still some more smattery of random pixels. And we are not sure if they are differences or not. So the next process would be dilating these pixels. We are just blowing them up so that we can have a little more accurate data without having to assess all of the extremely small regions of data. At this point, we are determining the contours. A contour in computer vision is a continuous curve along the boundary of an object. So anywhere you would see pixels that are connecting to each other on the edges would be considered a contour. Any of these small single squares would not be considered a contour. So we are, again, filtering on every step. After we have calculated our contours that are above a score of 1,000, which is just an arbitrary number, there is a large amount of fine tuning in this process, we're able to draw our bounding boxes around our image. So you can see we have our 4 holes with the bounding boxes around them. We have our deformation in the original photo that we used to warp it, and then we actually have an extra little box down here, which we believe is some dust buildup. You can see it really got the grout lines to line up pretty much exactly correct, and there's a little piece of gray brick on the edges that it was able to line up as well. If we overlay the images at this point, and then swap back and forth, you can see how accurate the program is at really warping the image. This is almost exactly aligned except for maybe some of the dust that formed. And you can see that it knows exactly where the bounding boxes are. And you might notice that this box right here is a little bigger than the other ones. You can see how this hole pretty much is exactly around where the hole is, and then this bounding box has some extra room on the edge of it. That's because actually a piece of the wall broke off right here. So it's able to not only find large amounts of change, but small regions of change as well, something that the human eye might not see. And then again, we do have like a large amount of dust buildup over on that side.
We should point out, these are holes drilled to mount a television.
Yes.
These are not like 9-inch bolts that you're going to be mounting steel to a brick surface. These are actually, this is a fairly small hole within the context of the wall, shown writ large.
Certainly, yeah. And that is the process for our pixel difference calculation. Does anyone have any questions?
Is that me?
Nope.
How long, when you went back through the original stuff and you were going and it was processing, how long does it take to process each one of those? Is it minutes, is it hours?
It's probably 30 seconds.
Oh, okay, well that's not bad.
No, it's not.
Oh, okay, all right.
So it's not as fast as like the live webcam segmentation and things like that. I mean, that's actually pretty rapid to be doing. And really what we're contemplating within the context of this use case is not necessarily just using the live feed off the drone that the controller is using to guide it as it is power washing a building, but instead a photo stream that is generated later from that video feed. So wanted to focus in on like, how would we compare images?
Yeah.
There's potential as the technology advances to start just looking at the live feed, as Monica showed us. But this use case was pretty, it was unique. It was fun. There's a lot of great AI vision use cases. This is the one we did. There's also a lot of accessibility. There's an app that called Be My Eyes that is pretty wonderful that helps visually impaired people see. It used to be just a two-sided network between two people, but now it's a two-sided network between a person and an AI vision app. So helps people cross the street when they can't see. That's pretty amazing.
Yeah, that is.